system complexity, current challenges, and then how to tame the complexity, what we do at the moment, and a little bit about what's missing. As a starting point, this is a Stone presentation from DARPA, a DARPA AVM project. They looked at time to market in different industries. It's a little bit complex. The complexity is expressed as a measure of complexity in terms of parts and lines of code. It's logarithmic at the bottom. At the same time, it's a time axis. So we see former in time, like in the 1960s, very on the left, and now on the right. And we see that different industries have coped very differently with this in terms of time to market and coping with the complexity, the rising complexity of systems. The most complex systems in terms of this complexity measure are integrated circuits now, and they seem to work really well. The last time I remember a very public recall of an integrated circuit was a Pentium FDiff bug in the mid-90s. And I will also be able to give, I think, some reasoning why it has been such a long time. There are issues with manufacturing, but not with design, like with a Pentium. And we have the automotive industry, which manages to go to market faster than in the past, and the aerospace and defense industry, which takes forever to get anything done. Why? Sorry, it's true, right? Okay, and so we need disruptive changes. Things need to be changed, and we try to figure out what needs to be changed. So I give examples to talk about this complexity a little bit. This is a mobile platform system on a chip, next generation mobile gaming platform by NVIDIA, billions of transistors, hardware, software co-design, super complex, and still all of us, we just take our phone and play a game, and it works, and we expect it works, and nothing's wrong with it. And they come to market in no time at all, with new systems and higher complexity. And I'll come back to this. Human physiology. It's a system that would be extremely useful to use in medicine, in the pharmaceutical industry. It is super complex, and it's not used in modeling. I don't know a pharmaceutical company that uses a full human system model for checking validity of medicine. If we would understand that system, there would be no uncurable cancer. If you would be 80 years old, you would figure out what to do with the second half of your life. Right? But we don't understand it. We have no idea how it works. Or, well, we do have, very, very superficially, but we know lots of things. We don't know lots of things. So there are people that try to model these things. Graphics is all fine, but really the details, we are really far from understanding them. Second example from this, we are always talking about hierarchy in system, the heart as a subsystem in the human. There's supercomputer centers that specialize on modeling the heart. It's a combination of a sophisticated mathematical model and imaging technology that allows to take your heart into that supercomputer and figure out what to best do with it when it has a problem. Yeah? So this is, it's a subsystem model. And still, we don't have complete understanding. It's extremely complex, even just the heart. It's multiple scales. We need to understand the chemistry in the heart. We need to understand the full thing as just a simple pumping device. Yeah, we can build artificial hearts. But it's a detailed cardiac simulator. I have the weather model here as a very complex system that we are all affected from because there are global issues on climate change, and weather is very much known to this sensitivity dependence on initial conditions. So there are complex systems which have chaotic behavior. Weather is the best known one. We do have chaotic behavior and this high sensitivity to initial conditions also in engineered systems, never intentional, but when we discover them, we have really great problems, and it's nothing that we really want to have. So, modern commercial aircraft, this is the 787. I think that is about the latest larger commercial aircraft series that came to the market. From a systems engineering standpoint, it was a really big challenge. There was a lot of technology changes, carbon fiber fuselage, and all electric aircraft. The 777 has 400 kilowatts of electrical generation power on board. The 787 has over 2 megawatts, so more than 5 times the electrical power, and needs it. And it was a really step change because before, in the 787, the electrical system isn't safety critical. If the generator goes down, you're fairly safe for some time. Not so in a 787. The air is gone for breathing because they went from a bleed system, getting the air from the engine into the aircraft, to a compressor-driven system. So when the compressor's out, the air is gone. So everything became safety critical that wasn't safety critical before. Then, in terms of building this thing, there was the organizational complexity with the extended enterprise. So there was, it took lots of time to get it to work, to get the supply chain working for the systems. Modern automobile, that's about the system I know best, and I think the biggest issue here is software complexity. There's a very nice graph on informationisbeautiful.org on the net about lines of code, software lines of code. A modern car has over 100 million lines of code and instructions. That is an incredible lot. How many bugs are going to be in there? Can we guarantee it's bug-free? Remember the Toyota unintended acceleration? It wasn't software, or they couldn't determine if it was software, but they could say something. The software was so complex that they could not have exclude software. It couldn't be tested, it couldn't be proven. Another scary number here are the 500,000 requirements in total, 50,000 hardware, 450,000 in software, thanks to Richard Riff for this nice number. And the 10,000s of different variants that you can build from a single. Smart grid, or grid in total. This is the largest man-made system. Yeah? Boston to San Diego, one single system, can collapse in a few instances. And it did. Last time I was in the US for a longer time, 2003 was a large blackout going through most of the eastern US. And I'm a controls engineer. I talked to an expert on network stability. They don't know why it works so as often as it does. It's a system that we built that we don't fully understand. I can tell as much. And now we're trying to make it much more complex by getting feedback from all the consuming devices to control it better and make it into a smart grid. It's going to be a large challenge. Internet of Things. We're trying to connect everything to the internet. Smart grid is one subset of that, one example. Control and safety of the Internet of Things is going to be a big issue. Today, there is no safety at the bottom of the internet. I'd be scared if we have an Internet of Things without safety and security really in the foundation. So these are complexity issues which are really a little bit beyond of what we know. So we try to figure out different reasons for the complexity. Complexity through large numbers and scale. That's, for example, the integrated circuits. We know how to handle that fairly well. Network and connectivity complexity, human brain as an extreme example, maybe not, we're not quite there. Complexity caused by heterogeneity of subsystems, and I would count automotive and aerospace into that. That is a complexity that we don't have the tools to handle for. That's a reason why the aerospace industry is bad. And mathematical complexity, chaos, we have no ways of dealing with that really well. We can deal really well with large numbers, CFD and things like that. So I think I'll leave it here and give it to Steve for the moment.
And from what Brad tells me, I'll try to make it March. All right, so I'm going to talk a little bit about current state of the art in terms of how we try to deal with taming system complexity. So these are the examples that Hubertus has already talked about, and we see quite a variation in the relative maturity within different application domains where modeling techniques are used. Electronics being probably the peak. Medicine is the most complex of all of these, and that's where there's the greatest amount of work to be done. There are many good domain-specific tools, but when you start getting into modeling systems where real heterogeneity occurs, where very different sorts of physical domains and engineering effects are relevant, this is very nascent. It's very much in the beginning. This slide relates to some work that my company did in collaboration with Comet Solutions, bringing together a systems-level modeling tool with specific tools to model structures, thermal effects, and so forth. This is the sort of thing we need to be doing, but it's only very much at the beginning. In general, the single general principle we've found to attack these broader problems where we do have the heterogeneous effects is basically divide and conquer. It's hierarchical decomposition. When people think about how do I represent this in a human amenable way, in a general sort of thing, the most common approach has been these hierarchical block diagrams. So that's why we've got a zillion different tools that all look more or less the same. They've got boxes with lines connecting them. I've got my favorite, that's why it's in the middle. But there's a lot of these things, and all of these tools depend upon general systems theory. General systems theory is what is going to underlie our fundamental approach towards the original topic that we're supposed to address here, is how do we combine heterogeneous models in an automated and reliable way. That's what we're getting towards. That's the topic we were asked to advance. So this systems theory has been around for a long time. The terminology and concepts are very familiar throughout science and engineering, and this is both very good from the standpoint it gives us a good conceptual model to design modeling tools, but you also need to be careful because when you go from the conceptual model to an actual concrete tool, the meanings shift, and you need to preserve the generality that you need. So I want to be precise about what we're saying. We're going to use the term system, and that in effect means we're going to draw a boundary around some subset of what we're dealing with. Inputs and outputs, we really mean the system is surrounded by its environments. Inputs are effects of the environment on the system. Outputs are effects of the system on its environment. And the system internal to itself has its state and behavior. When we talk about a hierarchical decomposition, we're breaking the system into subsystems, and also that the larger system defines the environment for its subsystems. So it is in this setting that we can finally address, this is the original title we were given that we were supposed to address, is the ability to combine heterogeneous models in an automated and reliable way. And so the challenge is here. So we defined our terms, but how do we do this automated and reliable and make it work for all the different applications that we have? We have to ensure that it's general enough. We have to ensure that it is efficient so that we can actually run it on, and get real answers out in a reasonable way. We have to ensure that it's correct. And the open standards part is in order to make all these tools play together nicely. Whoops. So, sorry. The last part of this section, which we're going to have to do really, really fast, I'm going to turn over to Hubertus and see how much he can do in 40 seconds.
Okay, sorry. I'll try my best. This was these slides. I think I will talk about most of these in terms of open things. I have one particular thing. I want to go back here and really figure out in these different industries, why did some succeed, why did some fail? And so the audience is thinking, why are the integrated circuits so well? Dare to be more formal. They use actually formal methods to be able to prove that the systems are correct. They started using these methods in the mid-90s. They're using them now. They have formal descriptions of their systems. They have things that give you a mathematical proof that the system as described behaves correctly as specified. We don't do that in any other industry. What you see there in the specification, it's temporal formal logic. It was used, for example, to prove that the New York subway system software, the control software that controls how the trains are steered and signals, will not produce an unsafe situation with one sensor that is broken locally. And you can prove, as a mathematical proof on the software, that this will happen. It would be great if that would work the same way on our cars and the ABS software in that. It's not that case today. The second one, use open standards and APIs, because only then you will be able to really couple all the different tools that you need to use. So there is one open standard that's come up fairly recently. It's called FMI. It's a standard that allows to couple different system tools and even system tools to 3D tools for CFD and finite elements. And that will make looking at an overall system so much simpler than when all the tools design their proprietary interfaces, but when you look at an overall large-scale system, you still will need to do it. Okay. So now, for discussion, I have 3 questions here. No conclusions. So how should formal methods be combined with current systems engineering and finite element analysis, CFD, and multiphysics to move into the future? What are the missing pieces that have long lag times so that we have to work on today to make that happen? And how can we use existing open standards and languages to leverage to get there? Thanks.
Thank you, Hubertus. Thank you, Steve.